Okie doke. Today we're doing piecewise functions. Probably yesterday we did step functions, which were nice because they were just flat lines and it kind of had breaks in the graph, and it's like, oh, if x is less than 5, we're here. And then once it gets greater than 5, then you're down here. Great. Now we're going to have the same thing, except it's not just going to be a flat line. It's going to be slope-intercept form. So you're going to have to find the y-intercept and then use your slope, rise over run. So our lines are going to be a little slanted, a little diagonal here. All right. The graph at the right is the function f of x is x squared when x is less than 1. So if you look, x is less than 1 is to the left of 1, and there's the graph of x squared. Now, if that was the full graph, it would swing all the way to the right, but we only want the chunk of it that is less than 1. Now we don't have to graph piecewise functions quite that complicated. And then once it's between 1 and 2, it's just a flat line at 3, right? That was what we did yesterday. And then once it's greater than 2, you're graphing the line y equals x. So that would be starting at 0, going up 1 over 1, but we only want the chunk of that line to the right of 2. That's what we're doing today. Evaluating a function, though. They're going to give you an x to plug in, and you have to use the correct equation based on that x. So here's our piecewise function. F of x, y, equals 3x minus 7 if the x is less than or equal to 2. But if x is greater than 2, y equals 6 minus 2x. What? Let's see. All right, so they want to know, how about when f of 0, aka when x is 0. Well, which one does that fall into? X is 0, 0 is less than 2, so we would use this equation, 3x minus 7. And they're telling us that the x is 0. So we're going to do 3 times 0 minus 7. Done. 3 times 0 is 0, minus 7 is negative 7. That's it. It's just which equation are you using here? But how about if it's 2? Would that fall into the first equation or the second equation? Well, 2 is less than or equal to 2, so we're going to use that first equation again. So we're going to be doing 3 times x is 2, minus 7. 3 times 2 is 6, minus 7 is negative 1. Okay, all right. And then the last one, they want to say, well, how about 4? Which equation do we use? 4 is obviously bigger than 2, so we're going to use this equation. 6 minus 2x, and the x is 4. So this becomes 6 minus 2 times 4 is 8. 6 minus 8 is negative 2. It's very important. Just make sure you're using the correct equation. We've done this stuff before where it's like, substitute in 5 for x and solve it. It's the same thing. It's just which equation are you using here. Cool? So there's one for you to try here. Go ahead and pause it, check back in when you're done, see if you get the same answers as I do. All right, 5 would fall into the second equation, negative x plus 3. That'll give us negative 5 plus 3, which is negative 2. Negative 4 is less than 5, so we're using this equation. 3x, 3 times negative 4 plus 5. Negative 12 plus 5 is negative 7. And the last one, 3 is less than 5, so we're going to use this equation. 3x plus 5. 3 times 3 is 9, plus 5 is 14. Cool. Now we're going to graph them, baby, and we're having fun. Oh yeah, we're having fun. Cool. So we have a dividing line at 1. X is less than 1, we're graphing one equation. When it's greater than or equal to 1, we're graphing another. So I like to put an invisible vertical line where there's going to be a break in the graph. You don't need to do that if you don't want to. So when it is less than 1, to the left of that line, we're graphing the equation y equals 2x plus 1. Now that would start at 1, the y-intercept, and then our slope's 2, so you'd go up 2 over 1. And you could keep doing that. But we only want the portion of this that is to the left of this line. So that would kind of stop there. But we could backtrack too. We could go down to left 1 a few times. Great. Now, there has to be a dot at the end of it. Is it going to be an open dot or a filled in dot? Well, this is just less than 1. So that would be an open dot at that border there. Great. But once it is greater than or equal to 1, to the right of that line, we're graphing the equation y equals negative x plus 4. So usually that would start at positive 4, right there. And it would go, the slope's negative 1. So you'd go down 1, right 1, down 1, right 1, down 1, right 1. We only want the portion of this line to the right of our dividing line, which is positive 1. So that would start here and be all of these points. It has the or equal to, so that would fill in the dot. And you're like, oh, but Mr. Plant, there was already an open dot there. That's okay. It was an open dot for one of them. It's a closed dot on the other. So it actually doesn't matter which equation because it's in the same place. So you could just go ahead and fill in that dot. We just piecewised that function, dude. Look at that. That was fun. Let's try another one. Ooh, this one's nice. Our dividing line is 0. That's just the y-axis. So to the left of it, when it's less than 0, we're graphing y equals x plus 3. You would start at 3, and the slope is 1, so you'd go up 1, right 1. But we only want the portion to the left of this y-axis. So instead of going up 1, right 1, let's just go down 1, left 1 a few times. So that would be all of this stuff. And that is less than or equal to, so that would get the solid dot on the end of it. But once we are greater than 0, we're going to graph the line y equals 2x. The y-intercept there is 0, and then the slope's 2, so you'd go up 2 over 1. And it was just greater than, so that would get an open dot on the end of that line. That was fun. Really fun. Ooh! Now our dividing line is at negative 1. I'm going to actually draw it in because I'm feeling a little rebellious. So negative 1 is going to be our dividing line. When it is less than or equal to negative 1, to the left of that line, we're graphing the line y equals 1/2 x minus 4. If we were just graphing that line, you'd go down 4, and then the slope is 1/2, so you'd go up 1, right 2. You could do that. You could graph the full line. Now, we only want the part to the left, so we could also go down 1, left 2, down 1, left 2. If you want, you could draw the full line with a ruler and then just erase the stuff to the right of that dividing line. So this is kind of weird because it kind of starts like halfway through there. And then that was less than or equal to, so that would have a solid dot on that wall. Beep, boop. There we go. Oh, kind of erased my dot. Now when it is greater than negative 1, we're graphing the line, the equation y equals x plus 2. That would start at positive 2. The slope is 1, so you'd go up 1, right 1. You could also go down 1, left 1. So this would be that equation, and that was just greater than, so on the end there's going to be an open dot there. So again, like which line would it belong to if it was exactly negative 1? Well, if it's on that wall, you got to go with the solid dot, so it would be part of the green line if it was exactly negative 1. All right, here was going to be day 2 of the notes. We're just going to keep pushing through here. So here our wall is at negative 1. When it is greater than or equal to 1, okay, they're starting with a curveball. So when it's to the right of that line, we're going to graph the equation y equals 2x plus 3. That would start at 3. Then our slope's 2, so you'd go up 2 over 1. You could go down 2, left 1. We only want the portion greater than negative 1, so that would be to the right of this. And it was greater than or equal to, so that would end in a solid dot on that wall. Now when it is less than -1 to the left of that line, we're graphing the equation y equals -3x plus 1. That would start at 1, and the slope's -3, so you'd go down 3, right 1, but we only want the portion to the left. So we're going to have to go backwards. We're going to go up 3, left 1, up 3, left 1, up 3, left 1. We only want this chunk of that graph. And that was less than, so it's going to end in an open dot. So which line would it belong to if x was exactly -1? Right on that wall. It's going to belong to the black line because that's the one that has the solid dot, the or equal to. Here we go. We have it for when x is less than 2 and when x is greater than or equal to 2. So 2 is going to be our break in the graph. To the left of it, when x is less than 2, we're graphing y equals x minus 4. You start at -4. Your slope is 1x, so your slope's 1, so you'd go up 1, right 1. We only want the portion to the left of this line, so we could also go down 1, left 1. And that one is just less than, not the or equal to, so it's going to have an open dot on the end of it. But once we are greater than 2, greater than or equal to, we're graphing y equals 3 minus x. Kind of a weird order there. If you want, you could rearrange it, -x plus 3. Unnecessary though. The constant, the number without the x, is your y-intercept. So 3 is going to be our y-intercept. Our slope is -1 because it was -x. So that would be down 1, right 1. We only want the portion of this line to the right of that break. So that would be all this stuff. And then it was or equal to, so that would be a solid dot on the end. If it was right on that border, if it was exactly x equals +2, does it belong with the black line or the blue line? Which one has the solid dot? The blue line. So there we go. There we go. Let's see what else we got. Ooh, writing a piecewise function. We're going to write 2 of these, and then you're going to try one. So I notice here that there's a break at 2. So we'll say f of x equals, we got our squiggles. We got 2 lines here. So if we look when it's less than or equal to 2, right, because it's got a solid dot there, so we'll say if x is less than or equal to 2, what would the equation be? Well, we need the slope and we need the y-intercept. I see the y-intercept is 0. That's cool. The slope is down 2 over 1. -2 over 1 is just -2. So you could say -2x plus 0, but you don't need the plus 0. So we'll just say -2x. Great. But once we are greater than 2, because it ends in an open dot, if x is greater than 2, this one's a little more challenging. So I see that the slope is up 1 over 1. So our slope is 1x. But like, what's the y-intercept? Well, we're going to have to kind of figure that out with some backtracking. If we know the slope is 1, we could keep backtracking, go down 1 over 1 this way, and it would cross at +4. So that would be the y-intercept. So x plus 4. Unbelievable. That was a challenge. So let's try this one. I see that this one has a break at 0. So we'll say f of x equals something, and I notice this first line to the left of 0 has an open dot. So that would be if x is less than 0. The one to the right has a solid dot on the end, so that would be if x is greater than or equal to 0. So to the left, the slope, it looks like it's up 1 over 1, so our slope is 1, and the y-intercept is right at 0. So it'd be 1x plus 0, which if you clean that up is just x. But once you're greater than or equal to 0, different equation. I see the y-intercept is -2, so something x minus 2. The slope is up 1 over 1, so it'd be 1x minus 2, which is just x minus 2. These are challenging, but there's one more in the notes. It's for you to try. Go ahead and try it. Pause it and check back in when you're done. and see if we get the same thing. All right, so we got a break at -3. So f of x equals some stuff. That one's an open dot, so that would be if x is less than -3. And then this one's going to be if x is greater than or equal to -3. So I'm going to make this my blue line. I'll write the equation in blue so it might be easier for you to check. So the slope on this one, I'm noticing, is up 1 over 3. So our slope is 1/3. So where would that cross the x-axis? If I went up 1 over 3 again, boom, our y-intercept is -3. Our slope is 1/3. Our y-intercept is -3. 1/3 x minus 3. I'll do the other equation in green. So this slope is down 1 over 1. So our slope is -1. And we can clearly see that it just intercepts the y-axis at 2. So -1x plus 2, or -x plus 2. Look at us, piecewise in those functions. That's just how we do.